Math friends, this is AP Calculus, section 1.2, day 1. Today we're going to begin by reviewing the different types of functions. Most of these you have seen before in Algebra 2 and in Pre-Calc. Some of them you've seen, but you haven't really thought about how to label them. Okay, so just beginning with our table here, the first type of function we have would be a constant function. An example would be f of x equals something, 3, 5, -2. And this is just going to be a horizontal line somewhere along the y-axis and the coordinate plane. Domain of a constant function will be all reals. This lives everywhere in the coordinate plane. A power function is when our base is some number, that's our x, and then we have like squared or cubed or to the fourth power, to the fifth power. So the even power functions and the odd power functions tend to look different. Our even power functions are typically parabola shaped, W shaped, something like that. And again, these would be a domain of all reals. Our odd power functions, those are the ones that give us that snake shape where one end is down and one end is up, but domain is still all reals. Then we get into our reciprocal functions. These we looked at in pre-calculus. The reciprocal functions can either be even or odd. So first, 1 over x, where x is raised to the first power, or 1 over x cubed, or 1 over x to the fifth, that would be an odd reciprocal function. And these functions are always hyperbola shaped, and you'll typically, there might be transformations of course, but you'll have one branch in the first quadrant and one branch in the third quadrant, or opposite of each other. They could be in the second and the fourth, heading in opposite directions with an asymptote in the center. The even reciprocal function, so 1 over an x squared or 1 over x to the fourth, so on and so forth, those are going to have both branches either up or both branches down. So that's the difference between even and odd reciprocal functions. The even or the odd ones always have those branches kitty corner to each other, and the even always have both branches up or both branches down. Root functions we should be familiar with. So square root of x, fourth root of x, sixth root of x would be our even root functions. And these always look like some sort of a sideways parabola, but only half of it, right? Unless we have the plus or minus in front of the function, or in front of the equation. And again, if we had the bottom half of the parabola, technically a sideways opening full parabola would not be a function because it would fail the vertical line test. So if we're talking about it in terms of a function, then we can either just have the top half or just have the bottom half. Now our odd root functions, these are the ones that look like sleeping snakes, and we do have coverage of the entire coordinate plane, so the domain on those would be all reals. Whereas on our even root functions, the example previous, our domain is not all reals because we have this very specific starting point right here where the graph begins, and that is because we can't have negative values under even roots, and that prevents us from having our graph live everywhere in the coordinate plane. Polynomial functions we are very familiar with. These are your x cubes, x squareds. Our power functions fall under the category of polynomial functions, but here we typically have multiple terms, x squared, x constant, or x cubed, x squared, x constant. And these can look like all different things. They can look like parabolas, they can look like snakes, and they often have some sort of a wiggle jiggle in the middle, but we'll just use that as sort of a generic graph of a polynomial. I don't have any graphs in here for rational functions and algebraic functions because these can look crazy and they can look like just about anything. So I just put varies in there for those graphs. Our trigonometric functions, I think the big thing that you want to remember about trig functions is that they are periodic, so that they repeat over whatever their period is. They just continue to repeat. Our two favorite periodic functions would be sine and cosine, right? So there's one period of sine. If I wanted to draw another period of sine, it would look like that. And of course, this graph just keeps going in both directions. Exponential functions, this is when the variable is in the exponent and the base is a number. So again, do not confuse exponential functions with power functions. Those are two different things. And a typical exponential function has a horizontal asymptote at y equals 0 and then grows as the x values get larger. And then the logarithmic functions are the inverse of the exponential functions. So these have a shape that looks like that. Okay. And again, domain of our exponential functions is going to be all reals, but that's not going to be the case with logarithmic, because if hopefully you remember that you can't have negative numbers inside of a log. You can't take the log of a negative number. So that's why, unless there are transformations to our function, our graph exists only on the right-hand side of our y-axis. All right, so our first example is asking us to classify the following functions using the information in the table above. What type of functions are these? Well, letter A is pretty easy, right? If you see the word log, I think you should be pretty comfortable saying that this is going to be a logarithmic function. Letter B, we have g of x equals the fourth root of x. If you see a root, it's a root function, and since it's fourth root, we can describe it a little bit more in detail and say that it's an even root function. Letter C, we have 2x cubed in the numerator. We have 1 minus x squared in the denominator. So we have a polynomial upstairs. We have a polynomial downstairs. If you look at the types of functions, under rational function, you will see f of x is equal to p of x over q of x, where p and q are polynomials. So letter C, we would describe as a rational function based on definition. Letter D, we have a t squared, a t a constant. Hopefully right away you know that this is going to be a polynomial function. Letter E, be careful here. We have 5 to the t power. So on letter E, our variable is in the exponent. That makes this an exponential function. Because again, the variable right there is in the exponent. And then letter F, I see some trig. So that means that this has to be a trigonometric type of function. In example 2, we are given 4 curves on the same coordinate plane, and we're given 4 equations, and we're asked to match them together and explain why. Okay, so I'm going to kind of color code as I go here, and I'm going to begin with letter A. And letter A, the equation that they give us for letter A is y equals 3x. Well, y equals 3x is going to be a linear function. And we know that linear functions make straight lines, diagonal lines. So I'm looking on my curve, and I see the only one that is a straight diagonal line is this one right here. And so that one, which is capital letter G, is going to match with equation A. All right, letter B. Our equation is y equals 3 to the x power. We just talked about how when your variable's in the exponent, this is an exponential. So we're looking for something that has a horizontal asymptote at 0, and then as our x values get bigger, it grows. So that's going to have to be this curve right here, which looks like lowercase f is what they're labeling that one. Letter C, the equation that they give us is y equals x cubed. Notice that now our variable x is the base of our function. So this makes this a power function, and it is an odd power function. So we would expect that this is going to look like a snake. You look on the graph and you see here that snake-shaped function. That one is capital F. And then finally, letter D, is the equation y equals the cube root of x. And we know that odd root functions look like sleeping snakes. And of course, we only have one left anyway. So this is an odd root. Oops, root. And this is the one that we have left, which is definitely a curve for an odd root function. And that one is little g. So there we go. We have just matched the 4 equations with the 4 given graphs on that coordinate plane. We can use transformations to create new functions from familiar functions. The common transformations that we work with are vertical and horizontal shifts, vertical stretching and compressing or shrinking, and then horizontal stretching and compressing. And then, of course, we have reflections over our x-axis and over our y-axis. So we've kind of broken this down into sections. Notice that our textbook uses C as the value that identifies the transformation for every different type of transformation, which is a little bit confusing because in Algebra 2 and Pre-Calc, we use different letters for our transformations. We used A's and H's and K's, but your textbook just uses C for everything. So what you need to understand is it doesn't matter what the letter is that they give you in the equation. What matters is where it's located and what it means. So what I'm saying is when we look at our horizontal and vertical shifts here in the first box, and they're telling us C is a number bigger than 0, so a positive value, to obtain the graph of y equals f of x plus C, the plus C is after the function, you would shift your graph C units up, or if it's minus C, you would shift it C units down. So the big takeaway here is that vertical shifts are always outside the function or outside the parentheses. Okay, vertical shifts are outside, right here and right here. Right, the function is there and then the plus C is at the end or the minus C is at the end. Okay, well, what about horizontal shifts? Horizontal shifts, if you notice, are happening inside the parentheses, and those are our shifts left and right. So horizontal shifts are always on the inside of the parentheses. And it's the same thing with vertical stretching and reflecting. If we look at that, we can see that if we are going to be stretching vertically, so these are the first two are our verticals, okay, those are transformation is in front of the function. It's outside the function. Whereas when we talk about a horizontal stretch, we can see that that C value is inside. Inside those parentheses. So again, you have to look at where the number is. That tells you whether you're going to be doing a vertical transformation or whether you're going to be doing a horizontal transformation. And finally, it's the same with the reflections, right? If you're reflecting it over your x-axis, you see that that negative sign on that one is in front right here, right? Whereas if you are going to be reflecting over your y-axis, you see that that negative sign is on the inside of the parentheses. So again, don't worry so much about the letters that you used to be familiar with, but concern yourself with where is the number located in my function and what is that telling me about the type of transformation that I have? Is it a vertical transformation or is it a horizontal transformation? Or is it a vertical or a horizontal reflection? Using what we just learned in the previous two kind of boxes there, we're going to answer the following questions. It says, suppose you have a graph of a function f, and it doesn't matter what f looks like. All we know is that f is provided for us. Write the equation for the graphs that are obtained from the graph of f. So in letter A, they want to know, well, how would we write a shift right 2, and a reflection over the x-axis. All right, well, if we know that we are shifting our graph right 2, we know that that's going to be a horizontal shift, and that has to happen inside the parentheses. So we're starting with f, right? And it would normally be f of x, but if we're shifting it right 2, then it's going to be f of x minus 2. That takes care of our shift right 2. And now we have to show a reflection over the x-axis. Well, a reflection over the x-axis would be a negative sign, and that would be in front of our function. So we would put a negative sign right there, and then we're just going to write this as y equals. So this shows how we would transform our function f by shifting it right 2 and reflecting it over the x-axis. In example B, they want us to shift up 2. That's a vertical shift, so we know that that's going to happen outside of the f of x part. And then we're going to horizontally compress by a factor of 3. Ooh, that horizontal compression, those are the trickiest things, the horizontal stretching and compressing, because, and I'm going to put a little note here, this always looks opposite of what you expect. Okay, so if I'm starting with f of x, and I'm going to have my y equals here, if I am going to horizontally compress it by a factor of 3, and I know that horizontal things happen inside the parentheses, if I want to shrink it by a factor of 3, you would think it would be 1/3 x, but it's not. It's 3x, because it is opposite of what you expect. And if you remember from pre-calc, when we talked about this, it made more sense when we got to our unit on trig functions, and we kind of realized that, like, if you had sine of 2x, that was an accelerator. Like, it shortened your period. It made the graph happen twice as fast, which really is a horizontal compression. So if we're compressing our graph, we're going to be multiplying that x value by a number that's bigger than 1. Okay, so we have there f of 3x. And then if we're shifting up 2, we know that that happens at the end, so that would be a +2 outside of the parentheses. In letter C, we want to shift 1 to the left, and then we want to stretch it vertically by a factor of 2. Vertical stretches and compressions go in front of the f of x. So this would be y equals, if we're vertically stretching by a factor of 2, we're going to have 2 times our function. And then if we're shifting it 1 to the left, horizontal shifts left and right happen inside the parentheses. And again, opposite of what you would expect. So this is going to be x plus 1 if we're shifting 1 to the left. And then letter D, we want to reflect over the y-axis, and then we want to shift it up 3. A y-axis reflection happens inside the parentheses. So this one would be f of negative x. That's my y-axis reflection. And then the shift up 3 is going to be +3 at the end. Our last example, and this is kind of fun, we are given a graph on our coordinate plane, and we are asked to draw the graphs of the following functions based on the transformations. So we're just taking the graph that we're given and we're modifying it based on the transformations to the function. Letter A, I'm just going to color code this as I go. So letter A I will do in blue. Okay. And the only transformation for letter A is that -2 after the f of x, and I know that that is a vertical shift. This is going to be down 2. Okay, so I'm just going to take each point on my curve and I'm going to move it down 2. Okay, so that's our transformation for letter A. Letter B, f of x minus 2, ooh, that's got to be something horizontal because it's happening inside the parentheses. And since it's x minus 2, I know that that is going to be a shift right 2. So this time I'm just going to move each point 2 units to the right. So this point will be here, 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 and here. Okay, so there's our graph for letter B. Letter C looks like we have 2 transformations going on. We have that negative sign out in the front, which I know is an x-axis reflection. And then we have the 2 out in the front, which I know is a vertical stretch by a factor of 2. All right, so we can do both of these transformations at the same time. Basically, what we're going to be doing is taking our y values, like whatever the point is on the curve, and we're going to be multiplying it by -2. That's where the new point is going to go. The x values aren't going to change. Only the y values are, because both of our transformations have to do with the vertical, have to do with the y value. All right, so our first point on our curve is, the starting point of it is at -2, -1. So the y value is -1 right here, okay? I just put a little green dot there. So if I multiply -1 times -2, it becomes +2. So my new location for that point is going to be up here at +2. And I'm just going to continue to do that with each of my points. The y value right here is 0. 0 times -2 is still 0. So that point stays right there. This point right here, y value is 1. 1 times -2 is -2. So now it's going to go right there. This point right here is at 2. 2 times -2 puts it at -4. So that would be down here. And I know the point next to it will be right across from it there. And then my last point right here is at +1. 1 times -2 is -2. So here is letter C. This is the original f of x reflected over the x-axis and vertically stretched by a factor of 2. And then the last one is probably the trickiest one. So this one, I know inside I'm multiplying my x value by 1/3. So I know that that's that horizontal stretch or compress. But I also know with the horizontal, it's always opposite of what you expect. In the previous example, we did that horizontal compression and we multiplied it by 3. So now if we've got 1/3 times x, this is going to be a horizontal stretch by a factor of 3. And then that +1 tells me that I am moving my points up 1. Okay, so now the horizontal stretch by a factor of 3, basically I'm going to take my x value and I'm going to multiply it by 3. And then after I do that, my new location will be up 1 from where it's at. Okay, so again, starting at the starting point right here, I put a little orange dot there. My x value at that point is -2, right? So if I multiply it by -3, that's going to put me at -6 on my x-axis. And then right now, the y value is at -1. If I add 1 to it, it's going to be at 0. So this original point on the curve is now going to be at -6, 0, which is about right there, right above my h, okay, and stretch. And I'm just going to continue to do that. The next point on the curve, which is -1, 0. So I multiply -1 times 3. That gets me to -3. And then 0 plus 1 would be 1. So that point's going to go right there. This point right here, the original point is at 0, 1. So x value of 0 times 3 is still 0, right? But then I have to bump it up 1. So now it's going to be at 2. Okay, this point right here, which was at 1, 2. So I multiply my x value, which is 1, times 3. So now it's going to be at 3. And then up 1 will put me at the top of my graph. And then the point next to it had an x value of 2. So 2 times 3 is going to put that at 6. This is going to be off my graph here pretty quick. And the last point, I don't think I'm going to be able to graph because it's not going to be, I'm not going to be able to squeeze it on here. You can graph it on your paper though. the final point, the x value of my final point is at 3. So if I multiply that by 3, the x value is going to be way out at x equals 9. And the y value, which is at 1, is now going to be at 2. Okay, so my graph's going to go down, and that final point is going to be at 9, 2. Oops, sorry, I forgot to say up 1. All right, and that concludes 1.2 day 1.